Hello, in this video, let us talk about the traffic flow, which is a very good application of mathematical analysis. The network analysis plays an important role in electrical engineering. In recent years, the concept and tools of network analysis are found useful in many other fields, especially in the transportation system. Let us see how it is useful and how the application of linear algebra plays a main role here. We know that the system of linear equations can be represented by this n systems where x1, x2, etc., xn are n variables, and then aij, bj are all absolute constants. This system of n-dimensional vector will have n solutions. And this system of equations plays a main role, and there are plenty of problems in mathematics and applications require solving systems of linear equations like this. And so the concept and tools of network analysis have been found useful in many fields such as information theory and the study of transformation systems. The analysis of traffic flow through a road network during the pre period illustrates how systems of linear equations with many solutions can arise in practice. So let us see a system of linear equations which has got many solutions, which will model the traffic transportation. So this gives a typical road network diagram. Say it represents an area in downtown. The arrows indicate the direction of traffic flow. The flow of traffic in and out of the network is measured in terms of vehicles per hour, VPH, which is the vehicles per hour. Let us construct a mathematical model that can be used to analyze this network. So here, all traffic entering an intersection must leave that intersection. Say for example, if I take the traffic intersection A, the traffic in, there are two traffics in 610 and unknown. That must be equivalent to the traffic out, which is 450 plus another unknown, say x2. So the same way, for the intersection B, there are two inputs 400 and unknown and four outputs 640 and unknown. The same case with the other two intersections C and D. So the problem here is we are trying to find the amount of traffic between each of these four intersections. So if we take those unknowns as x1, x2, x3 and x4, we would like to know what these values x1, x2, x3 and x4 are. So at each intersection, the incoming traffic has to be equivalent to the outgoing traffic. So at A, we have 610 plus x4 must be equal to x1 plus 450. At B, we should have x1 plus 400 equal to 640 plus x2. And at C, I have x2 plus 600 equal to x3. And at D, I have x3 equal to 520 plus x4. So taking these equations pertaining to the condition that the traffic in equal to traffic out at each intersection, we get the final systems of equations in terms of x1, x2, x3 and x4 as x4 minus x1 equal to negative 160, x1 minus x2 equal to 240, x2 minus x3 equal to negative 600 and x3 minus x4 equal to 520. We can solve this system of equations using the substitution method, elimination method, graphing method, or even using the Gauss elimination method. If I'm trying to use my graphing calculator to make use of the reduced row echelon form of Gauss method, I may get the reduced row echelon form of this augmented matrix with the coefficients and the constants to be this equation 1, 0, 0, negative 1, 160, 0, 1, 0, negative 1, 1, negative 80, 0, 0, 1, negative 1, 520, 0, 0, 0, 0, 0. So the last equation is true, and from this preceding one, if I get x3 minus x4 equal to 520, and the previous one gives me x2 minus x4 equal to negative 80 and x1 minus x4 equal to 160. If I take x4 equal to t, then we may get the values of x1, x2, x3 in terms of t like this. I get x1 as 160 plus t, x2 equal to negative 80 plus t, x3 equal to 520 plus t, and x4 equal to t. As perhaps might be expected, the system of equation has many solutions. Many traffic flows are possible. A driver does have a certain amount of choice at intersection. Let us now use this mathematical model to develop more information about the traffic flow. Suppose if it is necessary to perform road work on a stretch, say at a particular intersection, it is desirable to have as small a traffic flow as possible in that stretch. So for example, if I am taking x2 equal to negative 80 plus t, and I know that it must be positive, that traffic flow must be positive. The flows can be controlled along various branches by means of traffic lights. What is the minimum value of this x2? Here, the answer, we know that all traffic flows must be non-negative. A negative flow will be interpreted as traffic moving in a wrong direction. If it is, in particular, if it is a one-way street, a negative flow will be interpreted as a traffic moving in a wrong direction on a one-way street. So we should have this traffic flow should be non-negative. That is, x2 must be greater than or equal to 0. If x2 is greater than or equal to 0, we get t should be greater than 80. So in which case, so we had x2, which is negative 80 plus t, to be greater than or equal to 0. So if I'm taking t to be equal to 81, then my x2 will be 1 because I want this to be greater than 0. So if by taking t as 81, that is my minimum value for t, I get the value for x1, x2, x3 and x4. So this will be my minimum value. The minimum value of x3, x2 must be 1 here in this case. So I am getting these values for x1, x2 and x3. So all these traffics are represented by the values what we get are VPH, vehicle per hour. In practice, networks are much vaster than the one discussed here, leading to large system of linear equations that are handled on computers. Various values of variables can be entered into a computer to create different scenarios. So for practice, there are several problems given here. We can use the same technique and try to find what is the unknown values x1, x2, x3 using the systems of linear equation. Hope this video was helpful. This video helped us to understand the traffic flow and how to use the linear algebra method to find the traffic flow values. That is, the vehicle moving in must be equal to the vehicle out in an intersection. Hope this video was helpful to understand the application of linear algebra, especially in the traffic flow, in controlling the traffic in streets. Thank you for listening and thank you for watching.